Good morning and welcome to Saturday Physics for everyone. Today I'm very excited to introduce today's speaker. We have Professor Ed Seidel, who is the Director of the National Center for Supercomputing Applications. He's also a founder professor in physics and a professor of astronomy. Ed has had a very long and distinguished career. He got his PhD from Yale University. Then he was a postdoc here actually at NCSA, where he moved up to a research scientist. He was the director of the Albert Einstein Institute, the head of the numerical relativity group at the Albert Einstein Institute. He was a professor at Louisiana State University. He was the director of the Skolkovo Institute in Moscow before he returned here to be the director of the NCSA here at the University of Illinois. And today he's going to tell us about actually some work he did back when he was the head of the numerical relativity group back at the Albert Einstein Institute. But specifically, he's going to tell us about gravitational waves, black holes, Einstein's theory, LIGO, and supercomputers. Let's welcome Ed.
Thanks a lot. Thank you. As you see, I have a packed agenda here today, but I'll try to make it fun. And I want to tell you about not only black holes, but really about Albert Einstein and the work he did. And perhaps the most important message of all is that although he's thought of as one of the greatest scientists of all time, the basic work he did was really based on very simple ideas. And I'm going to try to walk you through the simple ideas that Einstein came up with. And they sound simple, but when you follow them through to their logical conclusions, they're really totally revolutionary. And I illustrate my talk here with a picture from Physics Today. If you're a physicist, everybody reads this. If you're in the general public, I'll just point out it is the thing that really displays the great breakthroughs in physics. And this is from last August, and I'm very proud. The picture on here was actually done by a former student of mine. And one of the people who did the work in terms of the simulations, and this is showing black holes colliding that gravitational waves were emitted from, has actually been hired and now works here at NCSA. So just a lot of things, as you'll see, actually come out of the university here and out of the physics department. So let me give a quick preview. So what is all the excitement about? I hope you've all heard that in the last year, black holes and gravitational waves were discovered. So even if you don't know what they are, you've probably heard about that. So I'm going to describe a little bit about what they are, and I'll tell you kind of where they came from Einstein's theories. And let me just give a picture of Albert Einstein. I was very proud to actually lead the numerical relativity group at the Albert Einstein Institute, and I had worked here. In fact, I gave a version of this very talk about 20 years ago in this very room. And then a little bit later, I went on to work at the Albert Einstein Institute, which was just founded in 1995 in honor of Einstein. And about 100 years ago, in fact, exactly 101 years ago next month, he actually unveiled his theory of general relativity. And in spite of all of the brilliance and so on, he has this great saying, which he says, imagination is more important than knowledge. And it's just one of the messages, he has many of these brief sayings that are very, very deep. And he was one of the most imaginative physicists of all time. And he thought of things in ways that no one else thought of before. And I think maybe as an inspiration to all of us, when you think about the basic ideas he had, you think, I could have thought of that, but actually thinking it through all the way is the hard part. But they are based on simple ideas. So if you have a good idea, follow it through. That's the message from this picture. So if you were awake at all or alive on February the 11th, 2016, you would have around midday suddenly my phone just started sending me these messages. I was actually at the event where this was announced in Washington, so it was a very exciting announcement. I knew this is coming, but the front page of the New York Times, as I knew for years when this finally happened, that is the discovery of gravitational waves. There were experiments that were being done. There were simulations on computers that were being done of what the signals would look like and so on. The front page of the CNN, the front page of the BBC, and even the front page of the News Gazette. In fact, I particularly like this one because it mentions NCSA. So, discovery confirms Einstein's prediction, NCSA plays a role. And I'll get into this. Exactly what does that mean? I also want to point out, this is the spokesperson for the LIGO Scientific Collaboration. She's a friend of mine. I've known her since she was a graduate student, Gabriela Gonzalez. She's a professor at Louisiana State University, right next to where one of the detectors is that made this momentous discovery. So this is just a preview, and I'll get onto the rest of it a little bit more slowly. So let me back up. So the beginning of modern physics, by that I mean really modern physics, from quantum mechanics and relativity and so on, was Einstein. But let's go back before the beginning. Let's say about 1 billion years. 1 billion years before the beginning. And that is when, on this planet, multicellular life was just starting to form. So there's no way microbes are going to be able to understand what happened. And yet, so there's a race here going on. So 1 billion years ago, this happened. These two black holes, and this is a visualization from computer simulations. No one was there, and we weren't even capable of even thinking about this at the time. But let me show you the movie. This is the simulation of what happened 1 billion years ago. And this is the event that was actually seen last year. This is two black holes going around and around. And turns out black holes will bend light. And this visualization is showing as the black holes go around, the light coming from the stars behind it will be bent in this way. And so suddenly they come together, they form a big black hole. Now you might think, well, what's the big deal about that? So first of all, we didn't know if black holes really existed. We had no direct evidence of them until last year. We had no clear discovery of the actual gravitational waves that Einstein discovered. And I'm going to explain what they are in a few minutes, but we didn't know that. So that's the first time we detected them. So 1 billion years later, after this event happened, those waves came to the Earth, and we were just ready to detect them. Now, you have to think about the fact that life had to evolve on the Earth, too, for us to be able to be advanced enough to detect them. And we just made it in the nick of time. Literally by weeks. And I'm going to explain this in a minute. Okay. So let me give you, this is the hard part now, so you got to stay with me on this. I'm going to go through Einstein's theories and about 5 or 6 basic ideas he had that sort of led to the revolution in physics of the 20th century. So this is the first one. So Einstein, around 1905, came up with this idea of what he called the special theory of relativity. And the fundamental idea is that the laws of nature are the same regardless of your frame of reference. And what that really means is, let's say if you're in a car or on a train, and it's moving at a constant speed. That's the key thing, constant speed. So it's just moving along at a constant speed. So you're in your car. It feels like you're like in your house, right? It doesn't feel any different, really, unless let's imagine you have a very, very smooth car. So you got great tires, great suspension. You don't feel any bumps. So that feels the same. So Einstein sat around and he said, I can't think of any difference between the way physics should work if I'm in a moving car or if I'm sitting here at my desk. And he raised that to the level of a principle. It's a little bit different from saying I can't think of any difference. He said that's actually a principle of physics, that I couldn't tell the difference. So that sounds very simple. Now you combine it with another thing that was noticed around the same time. And this one is a little bit harder to kind of comprehend, but the speed of light is the same if you are sitting here still or if you are moving. And how can that be? So I'm going to illustrate this. So let's imagine this is a photon coming out of my flashlight. And who's going to catch it? I don't know if I can get it to you. Oh, sorry. All right, good. So that was a photon. Throw it back. All right, now imagine I were running at you, and as fast as I could. Now you kind of jumped back, right? Because you thought I was going to throw it. And so you think that you would add the speed of my running plus the football, and that's the speed that the football will be coming at you, right? And that's the way we learn to interpret relativity in our normal everyday lives. But it turns out that for a photon, it doesn't matter how fast the source is coming at you. It's the same speed. And there were equations that described the propagation of light that said the same thing, that it didn't matter how the source is moving, the speed of light given by the letter c is always the same. So how can that possibly be? You might ask, how can that possibly be, right? And why haven't we ever noticed that before? So you put those two ideas together, and without going into the details, I'll just say Einstein realized that a speed is basically the distance of something that something travels divided by the time it takes to get there. That's what speed means, right? So 60 miles per hour. You go 60 miles in 1 hour. So the only way that could possibly be true, that statement that Einstein noticed, or many scientists noticed, was that if you're moving, the way you measure distance and the way you measure time has to somehow change, or else there's no way that speed would be the same. So he worked out a mathematical theory of that, but that's the basic idea. So if that's the case, and he worked this out, those two basic ideas, you put them together and you can work out that moving clocks go slow. And it's not just that they go slow, I mean time itself goes slow, not just clocks, but time itself goes slower than a stationary clock. So just illustrated by this. Clock's going a certain speed, but the one that's moving with a velocity v, speed v, is actually going slower. And so it turns out that's actually true. It's been measured in many, many ways. People fly atomic clocks around in airplanes and they measure how much time has elapsed. They compare with identical clocks on the ground. The one that was flying around went slower. And there are other things like that as well that I'll come to in a minute. So the other thing is that rulers shrink. They shrink in the direction of the motion that they're moving. So if I had like a javelin, so don't worry, I don't really have a javelin. I throw it out. If it were coming at you, you would actually measure it to be shorter than it would be if it were standing still. And so those two facts come out of Einstein's special relativity. And so that sort of theory comes out. And it sounded amazing, and it is amazing, but it's actually true. So why haven't we noticed this? Because it sounds ridiculous, right? The thing is, at the speeds we normally travel, at like 60 miles per hour, that is such a tiny fraction of the speed of light that we just never notice this. If we routinely were going around in cars or planes that flew at speeds like close to the speed of light, there are much more dramatic effects, and it would be part of our everyday tuition. You say, well, of course moving clocks go slow, but it just doesn't seem like it because it's not part of our everyday experience. Okay, so that's special relativity. Normally it takes 2 or 3 weeks to cover that in a physics class. All right, so Einstein wasn't satisfied with this because that didn't include gravitational fields. So he thought about this. He thought about it a long time. He thought about this for 10 years. This is Einstein thinking about something for 10 years. And so he finally got it. And interesting, a side story is that he wasn't the only one thinking about this. In particular, there's a mathematician, David Hilbert, who was going at it as well. And in the final weeks, when Einstein's about to give his final talk in Berlin at the Prussian Academy of Science, he's afraid Hilbert's going to beat him. So he gives a lecture, but he hasn't actually finished his theory. And a few weeks later, he gives another lecture, and he made some mistakes. And so he finally got it and got it right, and he managed to beat Hilbert. But the difference was that he actually did it from basic physical principles. And I'll give you the principle. Hilbert had it from a totally mathematical point of view without the physics. So this is really motivated by physics. So this is another one of the simple ideas, the so-called equivalence principle. And it's a basic postulate that says if you're accelerating, as your speed is increasing, let's say you're in your car. So let's say you're in your car, the light's red, it turns green, and your mom just slams on the gas. So then you just sort of going fast, but you feel yourself being pushed back in the seat, right? You sort of feel that. You're being pushed back. Einstein thought about that and he says, I can't see how there's any difference between that and the gravity that caused Newton's, apple falls down and hits him on the head, says, oh, there's gravity. And so Einstein says these two things are actually the same. They're not just sort of similar, they're actually exactly the same, and he elevates this to a principle of science. Now, I can give you a homework exercise. You can go to your car and you can get a helium balloon. And let's say you go to the traffic light, and when the light turns green, you go. And what happens to that helium balloon? You're getting pushed back. It goes forward. Now, it seems like totally counterintuitive, but if it's like a gravitational field, gravity's pulling you back, So it's like, you're accelerating, but it's just like gravity. In fact, it's indistinguishable from gravity. So the balloon's got to go forward. And if you do that experiment, I've actually done it. It's like to see, does this really work? And it does. It really works. So Einstein said that that's the same as an accelerated frame of reference. So then immediately from that, you get the idea that if you think about an elevator, if an elevator is not just going up, it's accelerating up, and you have your flashlight or your laser pointer, you sort of shoot it across. As the elevator accelerates up, it'll look like the light's going down because it gets bent down by the gravitational field. It's the same as the accelerated frame of reference. So light is bent by gravity. And again, we've never really noticed this because gravity is so weak on the Earth. I mean, they only weigh 180 pounds and not thousands or millions of pounds because the gravity on the Earth here is relatively weak. But around something like a black hole, this effect is really dramatic. So this comes out immediately from this basic idea of Einstein's. Okay, so I got one more to put these together, and this is the most astounding of them all, which is a famous thought experiment. And this is in his original paper on general relativity. He thought about people on a merry-go-round. And he thought about how would different people on a merry-go-round measure time and space? How would they do that? So first of all, there are three key people in this. So you can do this experiment, although the effects will be too small. You won't be able to measure it probably. But somebody standing in the middle, the attendant standing on the side to make sure you don't get hurt, and then there's somebody on the edge riding around it, going around and around. Now maybe, I prefer another version of this. There's a thing called the rotor, where if you go to an amusement park, you go into this round room, it starts spinning around like a kind of a spin dryer in a washing machine, and you're pushed up against the edge. So you just feel that centrifugal force. It's just pushing you back. And so that's an accelerated frame of reference. And Einstein said, remember, he says that's the same as a gravitational field. So he thought about this. He says that's just like sitting on Earth being pulled. So the fact that you're being pushed out by that centrifugal force makes you feel like that feels like a gravitational field. He says that is a gravitational field. So then he says, let's look at special relativity that I just came up with. Remember, moving clocks go slow. So the first thing is, what happens? Moving clocks go slow. So the attendant and the guy in the middle, they're not moving with respect to each other at all, right? They're both standing, they're not moving, and they're not feeling any forces because this is a special one. He's sitting there in a chair and it's not rotating around, so he doesn't get dizzy or anything, doesn't feel anything. So therefore, these two guys, A and B, are in exactly the same situation. So they measure distances and they measure time exactly the same way. Okay? But this guy B is moving with respect to C. So he's going around. So his clock's got to go slower than C. But he's not moving with respect to A. So A has to conclude the only way this could happen would be clocks have to go slow in a gravitational field. So clocks go slower the stronger the field is, the faster the guy's going around, right? They go slower. So that means if you're like on a mountaintop, you're further away from the Earth, your clock will actually go faster than on the Earth because the gravity is stronger here. The further you away from the Earth, the less you feel it. So therefore, the clock has to be slowed down by the Earth's gravity. And so people can actually measure these things. So the astounding thing is, according to general relativity, clocks in a gravitational field go slow. And the same thing, you can make the same thing about the rulers. And I won't go through the details of it, but basically, distances also change around in a gravitational field. So the rulers will also change. And what that means is that simple things like the geometry. So you've all had high school geometry, right? So remember pi, it's the circumference, the ratio of the circumference to the radius of the, or the diameter, the radius of the diameter, anyway, one of those of a circle. And it depends actually on the gravitational field. So that's sort of the basic geometry that we have depends on gravity. So that means gravity warps space. It curves it. And so that comes out of these simple thought experiments that Einstein did. So those are the key points I want to teach you about what Einstein's theories were. Now, but then the implications are just amazing. So just remember this. Clocks, actually, time itself slows down in a gravitational field, and gravity causes a warp in space-time. It causes space to be curved. Now, how many of you have seen Interstellar? Okay, so if you haven't seen it, I have a slide at the end. I'm going to recommend you go see it. And that you also read Kip Thorne's book called The Science of Interstellar. That comes with it. But you remember, when they go onto that planet, they go onto the planet with the tidal wave, and remember, they're like, oh, we're near this black hole. Oh no, time is going faster, back where my family are, back on the Earth and so on. And then they come back, and lo and behold, they're a lot older than the people who went down there. That all happens. That has worked out. It's exactly according to this idea of general relativity. Okay. Those are the key physics lessons. I got a couple more to sneak in on you, but I'm going to switch gears a little bit. So Einstein then said, why do things move as they do? Why do things move? So, another prop. Why does this thing take that trajectory? Because it's going as straight as it can in a curved space-time. That's basically, and Einstein said, that's it. That's gravity. I've got a slide here to show this. That's a curved space-time. So, so two lines may be parallel, but they may do funny things in a curved space-time. This trying to illustrate that point. So in curved space-time, geometry changes. So Newton was one of the great scientists of all time as well, but he had this idea. So he wrote it in a formula. It basically says the force between two objects is related to their masses and blah, blah, blah. So it's mathematical theory, very good, explained a lot of things. And Einstein says, well, Isaac, you're right, but I think actually mass curves space-time, and then particles, or we, move in the straightest possible path between 2 points. But that space is curved by the gravity. So what does that mean, you might ask? Well, okay. That's the straightest line between 2 points, and that's what we're used to. That's the way we live. We live in this what's called Euclidean world. But on the surface of a sphere, it's curved. The shortest point path between 2 points is curved. It's called a geodesic in mathematical terms. So basically, it's obviously curved. You can't move off that sphere, and so the straightest point is actually curved. And that shows you in a curved space, things actually have different sort of curved paths, but that is the straightest path that you can take. All right, so that's basically the revolution in physics. Now I want to talk a little bit about black holes, because I mentioned earlier, what is a black hole? I talked about a black hole, assuming we've all heard of it. Now we've all heard about black holes, right? So something out there, a black hole, or my desk is a black hole, or whatever. Everything just sort of disappears inside it. Now what does that mean? Well, in real life, in the universe, what happens is very big stars, the more mass they have, the more gravity they have. And if they have a lot of mass, at the end of their lives, they might blow up, they might run out of fuel, different things can happen. But eventually, if there's enough mass left over and there's no fuel to keep the pressure up, to heat it up, it'll eventually collapse in, and nothing can stop it that we know of. Nuclear forces are all overrun, and they just come down, and it forms this very, very dense, potentially infinitely dense object. And so that means that the gravity around that's going to be really, really strong. So imagine taking all the mass of like 100 suns, or the entire solar system, and collapsing it down to a point. That's what we're talking about. And then being able to go near that, the gravity will be very strong. Now remember, I said light gets bent by gravity. That was that simple experiment with the elevator. You know that light has to be bent. So this is a black hole. And what happens is, inside the black hole, you can't communicate with the outside, because you try to send your radio signals out there, and that's just basically light, a different frequency of light. And so the radio signals try to get out, but they can't. They're blocked because gravity is pulling them back too hard. But if you're on the outside, then you can look at it, you can observe it, and so on, but you can't communicate. You can send information into it, but you can't get information out of it. That's the basic point of what a black hole is, and that's how that actually works. It turns out from just outside, there's a thing called the horizon, the event horizon of the black hole. And that, again, that was shown in the movie Interstellar. So there's a beautiful visualization of the horizon and of all the matter falling into that black hole. And so, if you're outside the horizon, you can still send things out. But, you know, that astronaut that's falling in, so he starts falling in, and eventually what happens is it looks like time slows down for him compared to the people who are in the spaceship outside. And it slows down so much, and in fact, it just sort of stops. He looks frozen. But to the guy, the astronaut falling in, he just zooms right through. It's because he doesn't feel the time difference compared to the other people. For him, it feels normal. And so that's basically how a black hole works. So now imagine you had not one black hole, but you have two of them. And they're going to collapse, they're going to smash into each other because they have so much gravity. And that's, as I'll come to in a minute, that's what we observed a billion years after it happened. All right. So I got another little physics lesson to give you. Gravitational waves. I talked about them. You hear about them in the news now, but what are they really, right? So, and this is another thing. So Einstein's thinking about this, like, wait a minute, I got another idea. This is really a fascinating story. So almost immediately after he published his theory of general relativity in 1915, he wrote a paper and said, you know, this theory actually predicts, I didn't realize it when I came up with the theory, but it actually predicts that there's these little wiggles in space-time. Remember I said like the geometry gets curved and time changes? Well, those little differences in space-time can actually move throughout space at the speed of light. And that came out of his theory. But he said the effect would be so weak, we could never ever measure this. He didn't believe they could ever be measured because the effect would be so weak. So he thought it was irrelevant. Then it turned out, about 20 years later, he thought about things a lot. 20 years later, he actually wrote a paper and says, I think I was wrong when I said that gravitational waves exist. Okay, and so he tried to disprove himself. And it turns out somebody, the way it works in science, you have an idea, you write a paper, and then you try to get it published. But they've got other scientists looking at your work to check, is there a mistake? Somebody had the courage to reject Einstein's paper. So, and it turned out that they were right. The referee was right. I'm sure Einstein was furious. But then Einstein realized, actually, I was wrong. So the point is, there was a lot of confusion for the whole century about gravitational waves. Are they real? Are they fake? Are they mathematical artifacts? Or whatever? Are they really physics or not? And so there was a lot of discussion with this. But anyway, they turned out to be real, and that's what this discovery was. And I just, by a sort of analogy, I want to point out how this works. So basically, if you take an electron, so a charge or any charged particle, and you move it around, you can think of it like shaking, you can shake it. What happens is it emits photons. And the basic theory that Maxwell had for how light actually works said, yeah, if you start moving an electron around, a charged particle, it'll emit light. Okay, and so I won't go into more depth than that, but Einstein found that his equations for relativity said the same thing about masses. If you take a bunch of masses on a spring and you just hit it like that, they'll start vibrating around. And he says they will emit these gravitational waves, which are these little distortions in space-time that actually propagate at the speed of light. But he said basically you'd never be able to measure it, and then he wasn't even sure it was actually right. But it turned out it was right. So that's sort of the next physics lesson that comes out of this. So it turns out you get more of this radiation according to the theory depending on two basic things. How irregular is the motion, right? So it has to be it can't just be like perfectly spherically oscillating in and out. That won't emit any waves at all, it turns out. But it could be sort of very violent, and also the speed of it as well. So there's the mass, the speed, and the irregularity of it. Those all go in. So the bigger, the faster, the more massive, and the more irregular it is, the more you'll get. So therefore, if we're ever going to see this, given that it is actually very weak, we have to look at like cosmic cataclysms, like black holes colliding, like stars blowing up, stars colliding, neutron stars, different kinds of exotic things, all kinds of crazy things can happen. We might just be able to see a signature in gravitational waves. And that was the hope that some scientists had starting around around the 1960s, people began to think maybe we could actually detect this stuff someday. And so then there was a long, long period of about 50 years of the development of the technologies, and lo and behold, we did. So we want stuff like that. We don't just want me. So somebody told me once, if I do this, I'm emitting gravitational waves. So if you follow like the quantum version of this, I have to do this for about 300 years to emit a single graviton. So it's like really, really weak, really, really weak. Okay. So this is a picture. I did my best to find a picture of Einstein looking confused. So this is looking at equations, and he's like, that's right, exactly. He's erasing things there, right. So he says, wait, I'm not so sure. I'm not so sure about this gravitational radiation. I'm not so sure. I can't, these equations, they're a nightmare. I can't solve them. They're too complicated. So let me show you how hard they are. So here's a blackboard with more equations, and they were so complicated nobody could solve them. So this is the curse of Einstein. He thought of the simplest possible ideas in physics, and they led to this very beautiful but complicated mathematics. And he actually says, don't worry about your difficulties in mathematics. I can assure you mine are still harder. Okay? And so it turned out, for a century, no one could really solve the equations except in special cases. Okay? And they look like this. And that's like page 1, page 2, page 3. These are nonlinear partial differential equations. So they're like the most complicated equations in all of mathematical physics. All right, so now you got like entire communities of physicists and mathematicians and technologists all working to try to build detectors to detect these waves, solve these equations so we know what we might be seeing if we actually saw something, and so on. And so a century of work, and it is amazing, a century, it was 100 years of development of both the theory to be able to solve the equation so we'd have an idea what it is we might be looking at so you can make a prediction, and the technology to actually detect it. And they all came together about the last 5 years. It is incredible. So I'll give you a little bit of that story. Okay. So what happens if you're hit by a gravitational wave? Remember I said it changes distances. So remember there's like this little burst of waves. That just means there's this part of space that's just sort of oscillating. It's doing this. So basically it would stretch you up like this and it would then squeeze you down like that, and you sort of go through this motion like this, okay? And so it does it very, very little. So you basically couldn't hear it, couldn't see it, but it would be like hearing. And so in fact somebody's calculated if the sun were to blow up as a supernova, it would actually, you'd be close enough to the sun, so it would be really bad. But the first thing would happen is the gravitational waves would come out, and you'd hear it. You'd be like, it would sound like a mosquito. It'd be about 700, 800 hertz. It'd be like, bzz, and you'd hear that. And then there'd be the cataclysm. So you'd have just a bit of a warning on that. So the way this works then, people built these detectors, and this is a picture of this detector in Louisiana. So the NSF, the National Science Foundation, funded the development of 2 identical detectors, one in Louisiana and one in Washington State. And they did this about 20 years ago. They approved this. And then they continued to build the technologies until last year they actually heard that little bzz, and I'll show you what that is in a minute, but that came from the 2 black holes colliding. But basically what happens is when a wave hits the detector, it causes the whole thing to oscillate a little bit. And I won't go into the details. It's interferometry of 2 waves interfering with each other, so I don't want to get into the details. But basically imagine the whole thing oscillates, except it oscillates at the level of less than the diameter of the proton in a nucleus. Less than that. That's how little it works. I mean, that's how little the effect, even from black holes colliding. But the technology is so advanced. This is why Einstein thought this could never, ever be detected. And I have friends who work in this field, some of whom told me even 2 years ago, really distinguished scientists, I won't mention their names, but they said, I don't believe LIGO will ever see anything because there's no way they can actually detect that. And these are people who worked in the field. So it gives you an idea of the controversy about the science, but there's no controversy about the discovery that was made. So this is one of the instruments that discovered those black holes that collided 1 billion years ago. Now, this is another quote from another great scientist who didn't believe in gravitational waves either. And he actually said, gravitational waves, I don't believe them. They propagated the speed of thought, which is a clever thing. But Einstein himself was confused about it. So it gives you an idea. This is why experiments have to be done, because the theory said one thing, but nobody had actually measured it. So you have to do experiments to verify the theory. Okay. Now let me switch gears for a few minutes, since I actually am the director of NCSA, the National Center for Supercomputing Applications, here on the campus. So Illinois has played a major role in solving Einstein's equations, and it has for a long time since this really got started. But there's one thing, I want to quote another quote from Einstein. So zeros and ones, that's what's in a computer, right? It's binary, just zeros and ones. And so Einstein had this saying. He says a theory should be as simple as possible. And so all of his theories are actually very simple, but no simpler. But now, zeros and ones, that's like really simple. And yet, the impact of computing on our lives, I would say, even as a physicist, is perhaps more profound than that of general relativity on our everyday lives. And so, think about that. Just zeros and ones, but being able to manipulate them very, very fast on supercomputers has really changed everything from the way we do science to the way our mobile phones work to things that, you have very advanced, basically what used to be supercomputers, in your cars, in your phones, in your watches, and stuff like that. So that's just completely changed. But so this goes back to then to Illinois. So there was a professor here who's now at the University of California at San Diego. But Larry Smarr was a professor actually here in this department, and he was trying to work on what do you think? Collisions of black holes, and he needed supercomputers in order to try to solve all those very complicated equations. Because it's basically math, and on computers you can do a lot of math really fast. So he was very, very frustrated that the United States didn't have any open supercomputers for scientists, for academics, physicists, say at this university or any university in America to work. But Germany did. So he was going to the Max Planck Society in Germany, outside of Munich, and he got really kind of fed up with it. So he wrote this famous proposal, and this is an actual picture of it. For us, this is like the Gutenberg Bible. This is like a picture of the proposal, and it's actually in the Spurlock Museum. It's in a glass case over there in the Spurlock Museum. And it actually was what's called an unsolicited proposal. So that means he just had this idea. So the National Science Foundation did not say, we're going to build supercomputer centers. But an assistant professor at this university said, we need them, and here's a proposal for $55 million, and I want you to fund this. And he told me the story. He actually showed up at NSF and had it in a brown manila envelope addressed to Director, National Science Foundation, and went in the building and says, where's the director's office? So that's a lot of very bold thinking. But NSF actually said, that's a great idea, and actually we're going to fund 5 of those, of which NCSA was the first. So to give you an idea how the federal agencies that fund science are able sometimes to respond to great ideas, this is one of them. And so this last year, we've celebrated our 30th anniversary. So it was 30 years ago in January that NCSA opened its doors because of Larry's famous unsolicited proposal. And so now, if you have a chance to take a tour around the campus here, this is the building that's across from the Hampton Inn on University Avenue, and that's the staff of about 200 very, very expert people. Some of them are faculty from the different departments here. Some of them are students and postdocs. Some of them are staff. We have a lot of expert staff who know how to use supercomputers. So it's the people that's the most important thing. But this computer at the bottom, I was telling somebody earlier, that's a picture of the so-called Blue Water supercomputer. That's our biggest machine in America for academic research today. That machine cost about $200 million just for the hardware. So the building, which is not in there, that building's too small. We have a picture up there of the actual building where the machine is. It's over by the football stadium, right there. That building cost about $70 million just to hold the supercomputer. So the computer cost 3 times as much money as the building, just to give you an idea how big that is. It has 500,000 processors. And so that machine is being used to solve all kinds of problems in science, in geosciences, in physics, in astronomy, social sciences, in every area. So now the way this works, now that we've solved Einstein's equations. I didn't mention that. We managed with computers over 50 years to actually solve Einstein's equations so that when 2 black holes collide, we can actually solve the equations. That's a picture of them. But we can solve them, and we can actually say if 2 black holes of 20 times the sun and 30 times the sun collide and they're spinning in a certain way, the waveform would look like this. And then you can go look at, in the observations, we have these detectors that can make these unbelievably precise measurements. Why do you think we have 2 of these, by the way? Because, yeah, what do you think?
Well, the gravitational waves might hit any part of the Earth at any time, and if there was only one area, then you wouldn't be able to measure that precisely as 2.
That's true. If you have 2 of them, you can measure more precisely. Also, if somebody just did this to the detector, it might look like a black hole collided, but that's not going to happen in exactly the same way at exactly the same at the 2 detectors. And so both of those things are true, exactly. So now we have a science where people are actually doing things on the blue waters and other supercomputers, trying to say, what would it look like if a star blew up, or if 2 black holes collided, or if a neutron star hit a black hole, or whatever. And what would it? And then these people are saying, okay, we think we saw something. Does it match what you've computed? And that's actually what's going on now. And so there are a number of people here who are part of what's called the LIGO Scientific Collaboration. LIGO is the name of these detectors. LIGO, L-I-G-O, stands for Laser Interferometric Gravitational Wave Observatory. So that's what that stands for. So that's happening now.
How long is that period of that wave disturbance?
It depends on the masses, but this is at the level, it's like in the 700 hertz range, kind of something like that. Okay. So this is actually a cartoon that actually I've been giving in talks for 20 years. This is what we said, we think it'll look something like this. The details are dependent on the precise masses and so on, but this is what it should look like. And then this is what happened. So newsflash, last year, this is what was observed. And look at this. And then look at the picture I showed. So when I saw this, I just couldn't believe it. It's like, this is actually what this LIGO saw. And this is in one detector, and this is in the other detector. So you know that it's a real signal. And in fact, from this, by doing the supercomputer calculations, you can say that waveform could only happen if one black hole that was about 30 times the mass of the sun hit the other black hole that's 35 times the mass of the sun at half the speed of light. And that happened. And so it emitted more energy than 50% more energy than all the stars in the universe combined over a very, very short period of time, of order of milliseconds, a tiny fraction of time. It did that. And so that energy propagated across the world, across the universe for 1 billion years. And meanwhile, life's evolving, finally in the last 100,000 years they have people, and then we got people who are coming up with general relativity, but they can't solve the equation. Then finally they can solve the equation, they build the detectors, and they turn them on. And so this is a true story too. They had the detector running in like a primitive form a few years before, and it didn't see anything. Then they upgraded the detector 2 years ago, and they were about to turn it on, but they weren't quite ready yet because there were still some noise sources. It wasn't quite right, but they were taking data anyway. And the director, the chief scientist, Ray Weiss, actually wanted to shut down the detector to say, wait a minute, I think we got to improve something on this. But people said, no, we should leave it on even though we're not finished yet. It was during that period that that those waves finally arrived, and then they saw it. So they saw the signal actually a couple weeks before they were formally supposed to be doing science with the detector. So it's an amazing story. And so there you go. This is back to the News Gazette, and then that's the waveform. And I'm really proud that I worked in this field. The most exciting day of my life was that discovery. I was there in Washington, and like a lot of us, there are like tears in our eyes. Like we knew what they're going to say, but just having it said. Here we go. This is Kip Thorne. That's Ray Weiss, and that's Dave Wrightsey, who's the leader of the project. Dave actually came and gave the colloquium. I've been trying to get Kip to come out here for a couple of years, but given all this hoopla, you know, he's been hard to get to come out here, but we're working on that. So just the last slide. If you want to learn more, and I'm going to tell you a little bit about the impact on our regular lives. So talk about our regular lives. Everybody here has got some device that tells them how to walk from here to the car. And so those things, it turns out, they wouldn't work if you didn't actually know about both special and general relativity. They're both needed for those devices to be accurate enough to locate you, because it turns out they have to deal with satellites that are going around. They're moving at high speed around the Earth. They actually have a different gravitational field as well because they're so far away, and you have to take into account those corrections. So if Einstein hadn't come up with this theory, that wouldn't work. On the other hand, let's say he didn't come up with this theory. Some engineers would have developed this, and it wouldn't have worked, and nobody would know why. And so perhaps they could have figured out general relativity from that. I'm not sure, but okay. I want to point out another thing. How many of you couldn't live without a web browser these days? You can't do almost anything. Web browsers, we use them all the time. That actually came out of NCSA. And it came out of NCSA largely because Larry Smarr was very focused on visualization. He wanted to know how you visualize information. And although Larry didn't actually come up with a web browser, some great students, undergraduates, and some staff here were working at NCSA, Eric Bina and Mark Andreessen, and they actually developed this thing called the Mosaic web browser. And if you look carefully and say Internet Explorer, it actually points out that it was based at the National Center for Supercomputing Applications. So a lot of things come out of the basic science that we do here that you just wouldn't realize how much it impacts your life. So just another point, go see this movie if you haven't. I actually bought it because if you buy the movie, there's a companion piece which is Kip Thorne. So Kip actually basically stopped doing science for about 5 years while he worked out all of the science in every scene. He actually came up with the original storyline for Interstellar. He worked with Christopher Nolan to build a movie out of this. He had a contract in the movie with the theater, the movie studios, that says no scene in this movie can violate any known laws of physics. Okay? And I'm going to check. And he checked every scene, and he has a book, scene by scene, where he has these 3 categories. Either I can calculate that exactly with theories of physics, and usually special or general relativity, like when they go down to the planet and they're worried that their life's going to all be dead when they get back because the difference in times, that's worked out exactly. And he wrote a book along with it that explains every scene. But anyway, the first one is either I can calculate it exactly, it's plausible, or I can't think of any reason why it couldn't possibly be true. So the 3 different categories. Coming back to imagination, there's a lot of imagination in this movie. And then the last thing I'll say is there are interviews with a lot of the people, including Kip and a bunch of others, at a website that I helped develop at the Albert Einstein Institute. It's about the face of science. So there are many, many interviews with me, or with Kip Thorne, with Cliff Will, and a lot of younger scientists as well. Scienceface.org. So check that out. Scienceface.org. And there are lots and lots of interviews, all sort of aimed at the general public, and it's a really nice website. So I know I went on a bit long, but I just want to say it's been a great year for science, really exciting year. Nobel Prizes will be awarded. Didn't quite make it this year because they were a little bit too late in the announcement, but next year I predict. A major milestone in the history of physics. Very exciting. Einstein was actually right. The thing to remember is his ideas are really very, very simple. They just have amazingly deep consequences. And Illinois has played an important role in this, as in many other areas of science, and particularly physics. So thanks a lot.
We have lots of time for questions, so let's start with.
So, because of the diagram of the event horizon, and it showed gravitational waves escaping through a black hole, would it be possible to encode a message in those gravitational waves?
Yes, it would be. If you were able to manipulate the matter in exactly the way you wanted to You could use it as sort of a transmitter of information. You could. Yep.
Well, you know how if something goes at a certain speed and covers a certain distance faster than a blink instant, and is pretty much everywhere and nowhere at once, and how gravity can manipulate light in such a drastic way in a black hole? Well, couldn't you consider gravity almost like a speed, but faster than speed? Like an all-around force that manipulates whether how fast something is going, how much mass it has, and how the particles behave in a certain field of, let's say, liquids or something like that.
Right. Well, let me answer. I forgot to repeat the first question, which was, could you, by manipulating matter, could you encode information into gravitational waves to sort of send information out? So the answer is yes. If you could move it just the way you wanted to, and it was big enough and and fast enough, then you could send out Morse code out of gravitational waves. You could do things like that. So, and then the other question was really about. Could you think of gravity, maybe, see if I can get this right. Could you think of gravity as sort of like a super force that causes everything to move, or also is responsible for speeds and so on? And yes, that is true. And if you may have seen, or maybe not, but we had a colleague of mine, Miguel Alcubierre, come here and gave a talk at the opening for the 30th anniversary of NCSA a few months ago, where he talked about the warp drive. And so, actually, it's a very complex last name. His Mexican last name, Alcubierre, is his name, Miguel Alcubierre. But if you search for him, he worked with me up there at the Albert Einstein Institute. He actually wrote a paper giving the underlying science for how a warp drive could actually work. And so he's very famous in Star Trek circles and so on. And so, but basically says if you have a certain kind of exotic matter, and I can't tell you if that matter could be real or if it violates some laws of physics, but if it had these particular properties, then I can show you how to build a warp drive so you can actually travel in effect faster than the speed of light.
And you know how a Higgs boson has been discovered and how it's responsible, like anything that has mass, it's the particle itself,
Mm-hmm.
and how photons are also Higgs bosons.
Mm-hmm.
Well, a black hole should be able to then emit tons of Higgs boson particles, and when light comes towards it, instead of taking in the light, it should take in the light itself, but release the photons as some sort of Hawking radiation in a different form.
Okay, well that's getting into pretty complex physics there, but I would say, yes, there's a thing called Hawking radiation. That was one thing you mentioned, where basically the basic idea of Hawking radiation is you've got these particles that are being created in the vacuum all the time, and like pairs of them, like electrons and anti-electrons, but then they go back into the vacuum. But if it happened right at the edge of a black hole, one of them might get caught inside the event horizon and the other one could get away, and then that's how it evaporates. So there are lots of weird things about black holes, and then you talked about the Higgs boson, the fact that it has so much mass, and the Higgs boson gives particles mass. Generally the black holes are treated as classical objects, meaning don't take into account quantum mechanics, so I don't know about what the implications would be on the Higgs boson, but that's an interesting question. Let's take some others. Go ahead. Oh, thank you. Thanks a lot. Okay.
From what I understand, you're saying that only an accelerating mass is what is emitting the gravitational waves. So a stationary or moving and not accelerating mass does not, so this does not necessarily address how gravity itself actually works.
Well, so the thing about the acceleration is that was in Einstein's theory to say if you're in an accelerated frame, it's just the same as being in a gravitational field. So that's one thing. And then the second thing is about things moving around, then emitting gravitational waves. And so they have to move in a particular way, but most kinds of motions will do that, and then they will emit gravitational waves. So I'm not sure if that clarified your...
Stationary object, all stationary objects, is that how they detect each other via gravitational waves? Is that just a what comes from the
Oh, I see. Yeah.
We're now trying to figure out how gravitation actually works with each other and how things detect one another. Is that actually gravitational waves, or is that something different?
It's something different, but it's the fundamental force would be mediated by exchange of gravitons, and so in the quantum picture. But so at that level, I think you can still think of it as Newton did, which is sort of in effect a very good approximation to Einstein's theory. So, question? How about here?
You mentioned how they calculate when two black holes collide. But let's say you have multiple colliding, more than two, modeling that. Would you need a computer, or is it mathematically doable by hand? Or how does that?
How you would find, let's say, the signals that would come from multiple black holes colliding. Yeah. So the question is whether or not you could do that by hand or if you need a supercomputer to do that. There are some basic approximations that you can use to Einstein's theories that allow you to get pretty far with, without using a supercomputer. But to get the details, you've just got to do the full nonlinear equations, and that's what you need a supercomputer for. Mm-hmm. Go ahead.
My question is related to that. How would they possibly calculate all the possible combinations with this? Because each one probably takes a really long time, but then you can have different masses and different speeds.
Yeah.
Things of that nature. So how could they do that?
Yeah, so the question is, how can you possibly look for all possible things that you might observe with the wave detectors? Because in fact, each of these calculations does take a long time. In fact, it's on the Blue Water supercomputer, people are actually running things that can take days or weeks or even months if you want to put all the physics in, like for a complicated supernova calculation, for example. And then you get out one waveform, right? So there are what people are doing is what they call reduced order modeling, where they sort of run a bunch of different things as accurately as they can, and then they try to develop approximations that kind of interpolate between the different sorts of scenarios, two black holes of 10, 20, 30, 40, 100 solar masses or whatever, or neutron stars. And then people are trying to run parameter sweeps. So they say, let's run 1 million simulations on all the supercomputers we can get our hands on, and then try to create a catalog of waveforms. But they know the most likely things they think would be black holes, or we think would be black hole collisions or neutron star collisions that we would see. So they're focusing on those kinds of things. But the most exciting thing is, what have we never thought of before? And so that's where, when something comes and we see it, and you're like, what on earth is that? Then we're going to learn something really new about science. Okay, question in the very back on the left. Okay.
Were there any good arguments against the theory of the gravitational waves before the experiment was done?
Yeah, there were. So people thought there are complicated things in the theory that are called gauge effects that aren't really physics, but they're just like a choice of coordinates. And people thought maybe it's just like your coordinates are actually moving, but they don't carry any real physics with them. So for example, and so it was only around 1960 that it was proven that a system that emits gravitational waves loses mass, physical mass, and therefore it's real. It's a real physical effect. So there was a lot of discussion in the literature, including with Einstein himself being confused about this issue for a long time. And then once it was sort of proven theoretically, then the question is, will they emit enough waves, enough energy, and will we be able to make sensitive enough experiments to ever detect that? And that was not sure. In fact, it's amazing. The first proposal for LIGO in the 90s, the one that was finally funded by NSF. So the National Science Foundation agreed to spend hundreds of millions of dollars on a project that in the very abstract, on the first page, it says, it is highly unlikely that we will detect anything in the first generation of this detector. And they still decided to fund it. So, in fact, I asked the director in a public forum when they unveiled the detector, the advanced detector, I said, do you think NSF could do this now? And I was trying to be a bit provocative because I think NSF needs to be, really go for the long ball, do the really exciting stuff and don't have to have guaranteed success. And this is certainly a case for that. Over here. I'm sorry.
How long ago did these two black holes apparently collide to create these waves? And also, has LIGO detected any more of the gravitational waves after this event?
Right, so the question is how long ago were these detected, and has LIGO detected any more? So yeah, this particular pair of black holes did collide about 1 billion years ago, like 1.3 billion years ago. We don't know where. The detectors, actually, they don't tell you where. They just say, it's like suddenly, a bell starts to ring and you don't know where it came from. The detector starts ringing when a wave hits it. 'Cause if it hits it from here or it hits it from here, it doesn't make much difference to the detector. So even with 2 detectors, you get more directional, but you still can't tell. So we'll never know probably where those black holes were in the universe, but we know that they were out there somewhere, like in a big swath, somewhere out there about 1 billion light years away. And have there been any more detections? Yes, there have been more detections. One of them was published, and so there was a second event that was published, the so-called Boxing Day event, because it was discovered the day after Christmas last year. The first one was discovered on September, I've forgotten now the exact date, but 20-something. Who remembers the exact date? I can't remember now, but anyway, so these details matter to us. And then there are some other events where they're just not sure if it was really a signal or maybe it was a little bit of noise in the detector. But the detectors are being improved, and so they're not actually taking data. This fall, they're just starting back up again. And so they will be more sensitive. And there's another detector in Italy that will also be operating at the same time called Virgo. And with these 3 detectors, with improved sensitivity, we should be seeing events like this like every week, something at that frequency.
There was some questions over here.
Thanks.
Yeah, I'm curious about the prehistory of those 2 sort of 30-mass black holes. Where did they come from? I mean, one thing, is that the kind of thing we were expecting, that we'd have several tens of solar masses? And did they originally come from larger or smaller black holes, or was it just an accretion process from a single, supernova?
Yeah, good question. So the question is, where did these black holes come from, the ones that were actually observed? And so they're in roughly the 30 solar mass range, so 30 times the mass of the sun. So frankly, I wasn't surprised at that, because 20 years ago, when we were really, some of us were really making these calculations of what it looked like, that was the kind of numbers we talked about. But the astrophysics was very uncertain about whether or not you'd have stellar mass black holes that would be that heavy, that would finally, so basically very massive stars lose a lot of their mass as they evolve, and towards the end, if they're going to form a black hole, the feeling was they'd either be a lot heavier than that or actually not as heavy as that. So it was a little bit of a surprise to sort of the modern day astrophysics thinking on this, but I mean they were there, so then that means. But the idea is they probably came from stars that were originally in orbit around each other. So they're orbiting, and then one of them eventually runs out of fuel, and then it dies and turns into a black hole, then the other one does, and then that's how this forms.
So I was thinking that they were formed with a mass of like 30 miles?
Yeah.
Okay.
Yeah. I mean, there could have been some accretion on them, but it wouldn't have been very much.
There is a theory. You expect to see these maybe weekly.
Yeah, roughly every week.
They're only a duration of less than a minute.
Oh yeah, they're very, very short bursts of energy. Mm-hmm.
Okay, if I can get another one.
Sure.
So it's hard to tell how far away things are. So how do we tell it's that far away rather than a lot further away and more energetic?
Okay, so there are from the experimental side, you can make certain measurements, and it's complicated measurement, and actually I can't tell you in any detail how that works. On the other side, though, on the theoretical side, when you do the calculations, you know how much energy those black holes would have emitted, and then you can sort of say, aha, then therefore, if we detected them with this amplitude on Earth, then they must have been that far away.
Time dilation have anything to do with your detection of these?
Time dilation, not really. It's more about the stretching of space that is caused. So when those waves are traveling, so there's a little disturbance, it's just, it's sort of doing this to space-time, and then the detector, it oscillates with it as well, and then that's what it's all about, yeah. It's about the interference pattern because of the time difference. If you make one of the, so basically I'll explain a little bit about how the interferometer works. So there's a laser beam going back and forth in one and there's another laser beam going back and forth in the other, okay? And when the wave comes in like this, it squeezes this one while it lengthens this one. And so then the path length here, this one's going to, because it's a little bit shorter, it's going to come a little bit earlier compared to that one. And then the interference pattern of the two waves allows you to determine what happened. That's how that works. Okay?
So you said that, well, we have two sensors now. You can't tell where in the sky it is. Once we have three or even more, would you be able to sort of triangulate the position?
Yes. So the question is, if you have one or two detectors, you can't really tell. So one detector alone can't tell you almost at all. Two detectors, it turns out, they can tell you within a couple of overlapping circles, because the question is, like, if you've got, you say, okay, the wave hit this one, and then a little bit later it hit this one. So then you can get some idea of the directionality, but it happens to be in these different circles if you work out the geometry. With three of them, it begins to tell you much more. Aha, it was in this little area, like right here. With four of them, and so on, you get better and better ability. So it turns out that that most of the detectors that have been planned were being built around a plane around the like U.S. latitude, because Germany's building one, Italy's building one, and so on. So you need something further away, like towards the poles. You need something in the southern hemisphere in particular. And so when I was at the National Science Foundation, it turned out, just by lucky coincidence for me, I oversaw the Math and Physical Sciences Directorate, and that's where the LIGO detector was being funded. So I worked very closely with the Indian government and also with the Australians to try to get one of our detectors down in the southern hemisphere. And so it turns out that India has agreed to do this. And so we actually built 3 detectors. We only operate 2 of them, but we built 3 of them. And so one of our detectors, that is from the NSF, is going to go into southern India, and it'll be operating in the early 2020s. And then, this is when it's going to get really exciting. I mean, it's already really exciting, but even more exciting, because you'll be able to say it's within a couple of full moons, you'll know where the gravitational waves are coming from. And then you can coordinate that with telescopes, and you can say, well, look over there. I can tell you exactly where to look. What do you see? And then you'll be able to look at optical telescopes with neutrinos, with cosmic, or all kinds of stuff you can look at then.
You mentioned the GPS came out of the work that you've been doing and stuff like that. With LIGO and stuff, where do you see other leaps in technology coming, or possible leaps in technology?
So the question is, with GPS being, in effect, coming out of general relativity. So I would say it didn't exactly come out of it, but in order to build it to make it work right, you had to know general relativity. That's really how that came out. But what other kinds of things will come out of this? So for example, I mean, the quest to solve Einstein's equations in the first place is what led to the creation of NCSA, which is what led to the creation of the web browser, and which is also what led to many, many other advances in every area of science. And so there are many, many things like this. We're sort of 1 or 2 steps away from the advanced LIGO development. There are much better lasers, better noise systems to isolate the noise, because if you kick the thing, you can't mistake that for black holes colliding, all of these kind of things. So there's also a lot of quantum mechanics now that's being done. It's the largest quantum mechanical object that we have now that we can study as a system. So there'll be sort of unknowable advances in science right now because of these advanced technologies. So there's another version of that talk where I show this, that GPS system, and there's a quote by Rocky Kalb which just says, who would have thought in 1930s that the shelves of Best Buy would be filled with quantum mechanics? And that's really true, so you never would have thought that. But
David Hilbert was a very good mathematician, so at what point in the development, presumably he started at some point with Einstein's theories of relativity, at what point was he able to almost leapfrog ahead of Einstein to complete the full-blown equation?
They were running at the very end. So Einstein had been working on this from physical principles, and he sort of had the basic ideas of the equivalence principle down right away. But turning that into if space-time is actually warped, he had to learn about differential geometry and all of this kind of stuff. And he actually worked with a number of mathematicians who helped him understand the math for this. And so it was only the very end when he actually was able to come up with this theory completely mathematically developed. Whereas Hilbert started with a different thing. He started from geometry, and he took an object that's called the Ricci scalar, and he just said, if I do the variation of this thing and set it equal to 0, what does that give me? So it's a variational principle, and from that it turns out you can derive Einstein's equations. But so he was able to do it basically at the same time of Einstein, because he knew that Einstein was working on this, but he didn't have the physical derivation behind it.
Yeah,
so
he only started after Einstein.
Yeah.
Einstein stayed at his house, explained what he was doing,
Yeah.
and Hilbert hadn't even looked at it
Right.
until after Einstein primed him.
Yeah, exactly. That's right.
So he basically took Einstein's idea and used his math. He was a better mathematician.
He was a much better mathematician than Einstein, so he was able to derive these equations, but from a mathematical principle, not from a physical principle.
But he wouldn't have done it if Einstein didn't tell him.
That's right. It came from Einstein. Yeah.
All right, I think there's one last question.
Would you be able to gravitationally lens gravitational waves?
Yes, you could. So the question is about gravitational lensing and about whether or not you could do that with waves. So remember I said gravity bends light, right? So if you're in a black hole, it bends it so much it doesn't even go anywhere. It just sort of goes in, right? But if you're near a black hole or even near the sun, and I had this in my talk, but I didn't have enough time for it. Light coming from a distant star would just sort of graze the sun, and it gets bent a little bit, and then it looks like the light's coming out from a different place. So it moves the appearance of where a star would be if gravitational, because of the gravitational field. So yes, and so then there are very famous things going on in astronomy now where gravitational lenses, that can actually intensify light. They can sort of focus light beams, so you can see things that you wouldn't otherwise see because there's gravity that's bending light and it's making it sort of all focusing like a magnifying glass. And so yes, it would also gravitationally lens the waves themselves.